In this course, we will be doing a system design for YouTube. The first thing that we'll do here is the functional requirements. There will be two types of users. One who consume the content, who are also called the viewers, and the second one who create the content, called as the content creators. So let's write functional requirement for each of those separately. For viewers, there are mainly two requirements. The first one is streaming, where a user can stream any video from the platform. And the second one is device compatibility. Our application should be compatible with all the devices such as mobile phones, laptops, computers, etc. There is another set of requirements for content creators. Content creators should be able to upload videos, and once the upload is successful, they should get a notification. So that's it for all the function requirements. Let's now move on to the non-functional requirements. There would be two categories of non-functional requirements. One for content creators and the second one for viewers. For viewers, there would be four non-functional requirements that we will focus on. The first one is low latency. We do not want the user to wait for a video for a long time, like lot of buffering or lagging. When a user watches a video, the experience should be very smooth. The second one is scalability. If we talk about YouTube, there are millions of users watching videos at a time. So we want that kind of scale. The platform should be able to handle a large number of users streaming many videos from all over the world simultaneously. The third one is user experience. Users should get the best quality while streaming. So let's say if I have a very good quality internet, I should see a 4K or 1080p video, not a 240p. The fourth one is availability. The system should be highly available. That is, it should be available 99.9999% of the time. That is the 6 nines. Now we move on to the second category of non-functional requirements, which is for the content creators. There are mainly three non-functional requirements that we should focus on. The first one is scalability. The platform should be able to handle many content creators uploading numerous videos at the same time. The second one is security. The platform should ensure that there is sufficient security of the content that is being uploaded by the creators. Nobody should have unauthorized access to those videos. And also, there shouldn't be any kind of piracy. The third one is storage reliability. We do not want to run into a situation where we upload something and it disappears. For content creators, that would be terrible. So we do not want that. This will ensure the uploaded videos are safely stored and guaranteed to remain on the platform and does not disappear. Now we move on to the capacity estimation. The first thing that we usually do is estimate the daily active users and monthly active users. So for our system, we'll assume that there are 100 million daily active users and around 2.5 billion monthly active users. Next, we move on to the throughput estimation. In the throughput estimation, we have two parts, the read throughput and the write throughput estimation. Let's first estimate the write throughput. So as per our functional requirements, there is only one way to write to our system, which is by uploading videos. And since most of the people are watchers and not creators, we will assume 1 out of 250 people actually upload videos on the platform. If you are confused how we got these numbers, these are just some reasonable assumptions that we take. Now coming back to the calculation, that would be around 100 million divided by 250, which is 0.4 million users upload video every single day. That is 0.4 million write requests in a day. Similarly, now we move on to the read throughput part. Now according to our functional requirements, we primarily have only one way in which a user can read from the system, which is when a user streams or watches a video. Now let's take a reasonable assumption here. Let's say an average user watches 10 videos in a day. So if one user watches 10 videos, how many videos will be watched by 100 million daily active users? Well, that number would be 1 billion. That is 1 billion read requests in a day comes to our platform. Now we move on to the storage part. Now according to our functional requirements, we mainly store the video data. Well, there would be metadata for these videos, but the huge chunk would be from the video content data. So let's assume average size of a video uploaded is somewhere around 600 MBs. And from our throughput estimation, we know that there are 0.4 million upload video requests per day. So how much data is stored in a day, that would be 600 MBs into 0.4 million. That comes somewhere around 240 TBs in a day. Now since videos need to be stored for a long amount of time, we can't really delete them right away. So let's estimate how much storage we'll need in 10 years. So total storage required in 10 years would be 240 TBs in a day into 365 into 10, which is 876 petabytes. Now we move on to the memory estimation. When we talk about memory, what we mean is we are estimating cache memory size. Well, everybody knows that accessing data from a database is very slow. That's why we use cache. And to estimate the amount of cache memory required in a day, we simply need to take some percentage out of the total storage. So in our case, let's assume the memory that we use is somewhere around 1% of the total storage. Since storing data in cache is very expensive, that is why we have this percentage somewhere around 1 to 3 or 5% max. So taking 1% of the daily storage, that would be 1 by 100 into 240 TBs, which is 2.4 TBs in a day. So we'll need 2.4 TBs of cache memory in a day. The last part in capacity estimation is network or bandwidth estimation. Network or bandwidth estimation tells us how much data flows in and out of our system per second. Do not confuse this with the throughput. In throughput, we were talking about the requests per second. That is, how many requests flowed in and out of our system. We never talked about the data. So there are mainly two parts of network or bandwidth estimation. The first one is the ingress. That is, how much data flows into our system. And there would be a second one, which is the egress. That is, how much data flows out of our system. Let's move on to the ingress estimation. We know for a fact that all the data that comes to our system in a day is eventually stored somewhere. So if we can somehow know how much data is stored in a day, we would know how much data came into our system, right? Now, from our storage estimation, we know that number. We know that we store 240 TBs in a day. Therefore, incoming data in a day is 240 TBs. So the incoming data per second would be 240 TB divided by 24 into 60 into 60. Why 24 into 60 into 60? 24 for the number of hours, that is 24 hours, 60 for the number of minutes, and 60 for the number of seconds. So 240 TB divided by 24 into 60 into 60, which is equal to 2.7 GBs per second. Now we move on to the egress estimation, that is how much data flows out of our system. Well, all the data that goes out of our system is basically how much data is read from our system. Otherwise, why would the data go out of our system? Someone need to read that data, right? So if we know how much data is being read in a day, we know what is the egress, that is how much data goes out of our system. Since we know from our throughput estimation that there are 1 billion read requests in a day, and from storage estimation, we know that average size of a video is somewhere around 600 MBs. Now if we multiply both of these numbers, that is 1 billion requests in a day, and into 600 MBs, that would be equal to 600 petabytes in a day. So now we know 600 petabytes are being read from our system in a day. But we need to calculate per second. So how do we do that? That would be 600 petabytes divided by 24 into 60 into 60. That is equal to 7 TBs per second. So our egress comes out to be 7 TBs per second. In summary, the data flowing into our system per second, which is the ingress, is equal to 2.7 GBs per second, and data flowing out of our system per second, which is the egress, is 7 TBs per second. Let's move on to the API design section. We will do the API design for each of the functional requirements that we had, that is uploading a content and streaming the content. Let's look at the API design for the upload content first. Now before diving deep into the API design for uploading a content, we need to understand one basic thing here. The videos that the client is trying to upload can be of 10 minutes or even 2 hours. So it's not feasible to upload a video in a single request. Multiple requests are sent to upload small chunks of the video. And in addition to that, there is video metadata as well. we need to upload the video metadata along with the video. Now we will try to understand all of the API design for uploading a content in two parts. The first part is when the user clicks on the upload button, a request is sent to the YouTube server asking to upload the metadata. Here are the details of that first request. The HTTP method is a post. Why so? Because the client is trying to create something new on the server. In this case, video or the video metadata. The second is the request endpoint. Endpoint tells the server where to perform that action. Since we are creating video metadata, we use /v1/videos endpoint of the server. /v1 is for versioning, that is version 1 of our API. And since we are creating video related data, we need the /videos endpoint. But in addition to that, there is one additional detail here, which is the question mark upload type equals resumable. Why do we need that? This indicates that we are uploading a large media file chunk by chunk, and it is useful because if the connection drops while uploading this large file, we should be able to resume the upload from that point, that is resumable. So in summary, upload type equals resumable tells the server to provide a resumable URL back to the client so that the client can use that URL to upload the video. Next comes the HTTP body. We have told the server to create metadata entry for the video, but we haven't provided the details of that video metadata. This information is stored in the request body. We will have details like title, format, etc. in the request body. So the overall flow until now looks like this. The client asks the server saying that I want to post a long video, and then adds the details such as HTTP method, endpoint and the body, and the server responds back with a resumable URL that the client can use. This URL is also called the session URI. The client can then use this URL to upload the video, and since the URL sent was resumable, the video upload gets paused or resumed based on the internet connection. Now let's understand what the second request looks like. Now the client has a resumable URL. It uses the URL to upload the content. This time each of the requests contains all of the small chunks of video, and those are getting saved to the YouTube server. So let's dive deep into the API design for that part. The HTTP method is put here since we want to upload the actual video data to the given session URL. Since endpoint tells where to perform that action, that is where to perform the upload, we use the session URI provided by the server in the first request. Now since we got the session URI in the first response, we will use that as our endpoint here. The endpoint looks something like this: /v1/videos upload type equals resumable and upload ID equals 123, let's say. We have already understood the v1/videos and upload type equals resumable, but what does upload ID equals 123 mean? Well, that identifies the session, that is, this session ID is 123. So once we have understood what the HTTP method and the endpoint is, we now move on to the HTTP body. The HTTP body would consist of the video data in binary format, that is zeros and ones. So to summarize, the client sends the first request asking YouTube server that they want to upload a long video. In that request, video data is being saved in the YouTube servers, and in response, the YouTube server sends a session URI. That session URI is being used in the second request where the client is trying to upload the video content to the YouTube server. Let's now move on to the API design for streaming a content. Since videos can be very large, it could be around 10 minutes or even 2 hours. It's not ideal to get the whole video in a single request. Multiple requests are sent to get each chunk of the video from the server. And all these chunks are stored at different locations in these servers. So to stream the entire video, the client needs to know these locations first. So what YouTube does is that when a client wants to watch a video, it first sends a manifest file with the locations. Manifest file is a file which has the locations of all these chunks of the video. So when the client first requests to watch a video, the server sends the manifest file. So once the client gets hold of that manifest file from the server, it uses that to fetch different chunks from that server. So let's try to understand this more deeply. The client asks the server, "Hey YouTube, I want to play this video." And the server responds back with a manifest file to the server, including each chunk's location in the server. This is the initial request that the client sends. So let's dive into this initial request first. So as we know, HTTP method tells the server what action to perform. And in this case, since the user is trying to watch a video, it should be a get action, get that video. Then there's endpoint for that request. This tells the server where to perform that action. We use v1/watch endpoint to tell the server we want to watch a video. And why v1? That is for version 1 of that API. So in response to that get action, YouTube server responds back with a manifest file. This manifest file is used in the second request to get all the chunks of the video. Now we know how the first request and response cycle looks like. So now the client has a manifest file. They can send streaming requests directly to the server. But one thing we need to understand before moving on to the second request. The video chunks that we are talking about are not stored in the server. They are stored in something known as CDN, Content Delivery Network. Simply put, a CDN is a server that makes it easy to load large assets like videos and media. It's much faster way of getting that kind of huge static data like videos. So the client sends a request to those CDN asking for that chunk. Let's dive into that API design part. The HTTP method here would be again a get, because the client is trying to get the video chunk. And since we are getting the video chunks from respective locations, we use those locations provided in the manifest file as our endpoints. Now there is one more interesting bit here. If you see, we are using something called as HLS protocol for getting video chunks from the CDN. HLS stands for HTTP live streaming. It is a very popular protocol for streaming. The benefit with HLS is that it allows adaptive streaming, meaning the quality of video can adjust based on the user's internet speed. For example, if someone has a very fast internet connection, they will get high quality video chunks. If their internet slows down, the video quality also drops a bit to prevent long waiting times for the video. This ensures video plays without interruptions. So let's say I'm trying to watch a 4K video. My internet connection is good for the first 10 seconds. I'm able to stream 4K directly from YouTube. And then all of a sudden my connection slows down. In that case, YouTube will send me 240p videos and not 4K. That is what the adaptive streaming means. So in summary, this is how streaming works. Client sends a request to the YouTube asking for the video. YouTube in return sends a manifest file back to the client. The client uses that manifest file to connect with the CDN and get those video chunks. This is done via the HLS. Let's now move on to the high-level design. We will do high-level design for each of the functional requirements here. We will do high-level design for uploading a content and for streaming content. Let's look at the high-level design of uploading content first. So as we saw in the API design, the upload video process has two main steps. The first request uploads the video metadata and the server responds with a session URI. So let's try to understand the high-level design for that particular part first. When the user clicks the upload button, the first request goes to the API gateway. You can understand an API gateway like a server that acts as an entry point, managing and routing requests to various services. It's like a receptionist at a hotel who directs guests to the right rooms, in this case different requests to different services. So when the request comes to the API gateway, it routes it to the content upload service via a load balancer. Then the content upload service adds the video metadata, that is title, format, etc. to the videos DB. And finally, the client receives a successful confirmation along with a session URL. So that's the high-level design for the first request that went to the YouTube server. Now we try to understand the high-level design for the second request, that is when the client has the session URL and tries to upload the video content. Here's what happens. Firstly, the client uses the session URL as an endpoint and sends a put request. This request contains the actual video content in binary format, that is zeros and ones. The API gateway handles incoming requests and routes it to the content upload service via the load balancer. The content upload service then stores the video content in the object storage. Object storage is a place where all the static and bulky data is stored, like videos and images. When the entire video is uploaded to the object storage, the content upload service adds an event to the message queue. A message queue is like a queue where tasks or events are added by one service, and then those events or tasks are picked up by other services so that they can work on it. It's like asynchronous messaging. So the content upload service adds an event to the message queue. That event contains the video ID. Now, why does the content upload service adds an event with the video ID in that? This is because the video ID recognizes the video. So next, if we have to do some kind of post processing, that video can be picked up using that video ID. The content processor, which is a workflow engine, pulls this event from the message queue for further processing. It's called a workflow engine because it runs a series of steps one after the other. Inside the workflow, there are multiple steps happening to that video. Firstly, the content processor workflow engine uses that event to retrieve the video from the object storage. Remember, the content upload service added an event with the video ID in the message queue. Well, that gets picked up by the content processor workflow engine, and it tries to grab that video from the object storage using that video ID. Then the content processor breaks down the video into smaller chunks. Each chunk is then divided into different formats, different qualities or resolutions. So for example, let's say we have 1 minute video that is broken down into 10 chunks of 6 seconds each. Each chunk is then converted into various formats and resolutions, different formats such as MP4 MOV and resolutions such as 4K, 720p and 240p. Well, content processor engine does a lot of things and we'll try to understand that later. But once content processor engine is done chunking the video and converting it into different formats and resolutions, it then stores it into the CDN, the content delivery network. Well, uploading all of these chunks into different formats and resolutions to CDN is necessary because it allows the client to access the video faster. Now, each chunk uploaded to the CDN has a location URL. The content processor saves these locations in the videos DB. Since the video processing is complete now, the content processor adds an event to the message queue to signal that the video processing is done, and that event is picked up by the notification service. Notification service pulls this event from the message queue for further processing. And finally, the notification service sends a notification to the client saying that the video upload process is finally complete. Let's now try to understand the content processor workflow engine in detail. So formally speaking, there are 4 steps here, and each step is handled by a service. First, the content chunker service retrieves the event from the message queue. The second step, it uses the video ID from the event to get the video from the object storage and then breaks it down into smaller chunks. The third step, it uploads the chunks to the object storage. And the fourth step, for each uploaded chunk, it creates an event with the chunk ID and adds it to the message queue. Why does it need to send an event to the message queue? So that the next service in the content processor workflow engine knows that there is something to work on. Now we move on to the second one, which is format converter service. After chunking, the format converter service converts these individual chunks into different formats, as the name suggests. Again, a question arises, why do we need to have different formats for a video chunk? Well, this is because different devices that we use nowadays are compatible with a certain format. For example, MOV files get opened on the laptop and MP4 on a mobile phone. So coming back, what does this format converter service do? Here are the precise 4 steps. It first retrieves the event from the message queue. What event? the event that the content chunker service sent in the message queue with the chunk ID. The second step, where format converter service uses the chunk ID from the event to get the chunk from the object storage itself. It grabs the chunk from the object storage. Then it converts into different formats such as MP4, MOV, etc. The third step, where it uploads the converted chunks to the object storage. And the fourth step, for each uploaded chunk, it creates an event with the chunk ID and adds it to the message queue. Again, we see a common trend here. The format converter service also added events to the message queue so that it gets picked up by the quality converter service. Now let's try to understand the quality converter service. After converting to different formats, the quality converter service converts these chunks into different quality levels. Well, we understood we need to save different formats for compatibility reasons, but why do we need to store different qualities? Well, saving different qualities of a video is necessary so that the user has a good experience with the video. For example, if the client has a good internet connection, they will be given a 4K video, and if they have a weak connection, they will see a 240p video. And that is why we store different qualities of a video. Now, talking about the precise steps that the quality converter service has, the first one is when the quality converter service retrieves the event from the message queue. This is the event that format converter service added to the message queue. Then the second step, where it uses the chunk ID in the event to get the chunk from the object storage. It then converts it into different qualities or resolutions like 4K or 720p. The third step, where the service uploads the converted chunks to the object storage. And fourth, for each uploaded chunk, we create an event with the chunk ID and add to the message queue, very similar to what format converter service did. If you would like to visualize how the processing for all these three steps looks like, this is how it looks. There was the original video and it got chunked into three parts, chunk 1, chunk 2 and chunk 3. And for each chunk, we have different formats. So let's say for chunk 1, we have chunk1.mov, chunk1.mp4. And after converting to different qualities, that chunk1.mov got converted into chunk1.mov in 4K and chunk1.mov in 720p and others. And very similarly for other chunks as well. And in the end, we'll have bunch of different video files with different formats and resolutions. So until now we are done with chunking, converting into different formats and resolutions. Now it's time to upload to the CDN. So that's what our fourth service is, CDN uploader service. The CDN uploader service retrieves these video chunks in different formats and resolutions from the object storage and uploads it to the CDN. Along with uploading to the CDN uploader service also saves these locations in the videos DB. So the CDN upload service has these four steps. Firstly, the CDN uploader service retrieves all these video chunks in different formats and qualities from the object storage and uploads it to the CDN. So those are steps 6 and 7. And now since each chunk has a different location in the CDN uploader service also saves these locations in the videos DB. That is the step number 8. And finally, since the video processing is complete, the CDN uploader service adds an event to the message queue to signal that the video processing is finally done. So if you combine all of those steps in the workflow engine, this is how it would look like. Now let's look at the high-level design for streaming a content. In the API design section, we discussed how video streaming involves three main steps. The first step, where the client sends a request to the server indicating that it wants to play a specific video. The second step, where the server responds with a manifest file. This file contains the locations of the small video chunks. The third step, where the client streams these small video chunks from the CDN using the HLS protocol. So let's dive into the details here. When the client sends a request to the server indicating that it wants to play a specific video, the server returns back with the manifest file. Also, it returns other necessary video metadata like title, creator ID, description, etc. etc. The manifest file from the server looks something like this. It lists the locations of video chunks in different locations and qualities for that video. So if we check entry for one of the chunks, let's say chunk 1, which is for the video from 0 seconds to 5 seconds, we have the field chunk as chunk 1, the parent video as video 1, the format as MP4, quality as 4K, and its location. Similarly, there are other chunks as well with different formats, qualities, and in a different location. The client uses the locations mentioned in this file to stream the video. After knowing the location, when the client requests these video chunks from the CDN delivers these chunks to the client via HLS protocol. And we also know that CDN contains these chunks in different formats and different resolutions. So when a client requests MP4 format, it receives MP4 chunks. And when it requests MOV format, it receives MOV chunks. Similarly, CDN also has different resolutions of the same video. So when the internet connection is weak for the client requests low quality chunks, that is 240p, 360p videos. And when the connection is strong, the client requests high quality 4K videos. Well, it's a very common situation to see when the connection fluctuates between strong and weak. In this case, the client will intuitively adapt. When the internet is strong, it will request high quality chunks, and when the connection weakens, it requests low quality chunks. This adaptive behavior ensures a very smooth viewing experience. This process is known as adaptive streaming, and the HLS protocol supports it very well. And that is why we use HLS so often in the video streaming. Now let's move on to the deep dive insights. The first thing we'll look at is the database selection. In order to decide the database type, here are some general guidelines that you can follow. But do remember that it's not always black and white. A lot of things depend on the project needs. But nevertheless, here are some general guidelines. The first one, when you need fast data access, NoSQL is generally preferred over SQL. The second one, when the scale is too large, NoSQL databases tend to perform better than SQL database. So you should go with that. The third one, when the data fits into a fixed structure, SQL is more suited. And when the data doesn't fit into a fixed structure, NoSQL should be your choice. The fourth one, if you have complex queries to execute on your data, SQL should be your choice. The fifth one, if your data changes frequently or will evolve over time, go for NoSQL. This is because NoSQL supports flexible structure. Now, if we look at our high-level design, we have one database that we need to decide on. That is the Videos DB. Now, Videos DB will have a very high scale. Why so? Because millions of YouTube videos are uploaded and watched every single day. So you can imagine how much content metadata is being fetched and then streamed. To handle such a scale of writes and reads, NoSQL will be preferred. Second, fast access. As per our non-functional requirements, we need low latency. And to support low latency on such a high scale, NoSQL will be suited. The third deciding factor would be the simple query pattern. When the user clicks on a video to watch the content, the server returns back the video metadata along with the manifest file. This is the main interaction with the Videos DB when we are reading video metadata by a video ID. NoSQL can handle this query pattern very easily. We do not have any complex query pattern here. So in summary, due to very high scale, fast access, simple query pattern, we will go forward with NoSQL. Next, we move on to the data modeling part, where we define the schema for each of the DB. In our case, we have only one database, which is the Videos DB. In Videos DB, we have four main parts. The first one is where we define the video ID. This is like a unique identifier for videos. The second one is technical metadata. This would include things like format, duration, etc., like the technical details of the video. Then we'll have the general metadata for the video. That would be creator ID, title, description of the video. And the final section would be content delivery metadata. This would include locations of all of the chunks in different formats and resolutions. So we'll call it CDN URLs, and inside that we'll have different sections for MP4, MOV, and within that MP4 we'll have different sections for 4K, 720p, 360p and so on. We'll store CDN locations of all of these chunks inside this. Now once we are done with the modeling, we'll talk about the common queries that could happen here. The most common query is when the user is trying to read the video metadata using the video ID. It occurs when the user clicks on the video to watch the content. The server returns back the video metadata along with the manifest file. So if you see, the video ID, the technical metadata and the general metadata would be the metadata sent to the user, and the content delivery metadata section would be sent in the form of manifest file. There is one more additional detail we could add here, which is the indexing. Well, indexing is like a shortcut to quickly access the data that you want. And since we have a common query to grab the video metadata using the video ID, we will make the video ID as our index. There is one more interesting deep dive we can do here, which is the HLS encoding part. So just to recall, the content processor workflow engine consisted of 4 different steps: the content chunking, the format conversion, the quality conversion, and the CDN upload. We also learned about HLS and how it enabled adaptive streaming, which allows streaming different formats for different devices and different qualities based on your internet speed. Whenever we stream videos with HLS, the video chunks need to be encoded in a certain way. What is this encoding? We talked about formats and resolutions, but what is this encoding? Encoding simply means turning the video into stream of zeros and ones. So let's say we have video 1. One kind of encoding can convert that video 1 into 0101, whereas another kind of encoding could convert it into 0111. So as you see, different encoding converts these video formats into different kinds of zeros and ones. So for HLS to work, the video needs to be encoded using specific standards like H264 and H265. So in our current workflow, we have the process of chunking, changing into different formats and resolutions, and uploading to CDN. Now if we want to use HLS, we would need to convert these video chunks into these different encodings. So how do we do that? We'll add an additional step for encoding in our workflow. So once the chunking is done, we were converting that chunk into different formats, right? But let's change things up a bit. Once the chunking is done, we'll add the encoding step there. So here's how it looks like. First, the content chunking is done. In the second step, encoding is done. That is, each chunk will be encoded in H264 or H265 standard. Then we'll do the format conversion, and the fourth step would be the quality conversions, and the fifth one, the CDN upload. This introduction of the encoding step ensures that our workflow aligns with what HLS needs, enabling adaptive streaming.